Let's see an application of these principles. We count surjections between two finite sets. As I recall, we have counted all maps between two finite sets. We have counted all injective maps and all bijective maps, which were called which is essentially equivalent to counting permutations. So the kind of missing field is surjections. And here is the answer. It's probably the most complicated of these answers. Let m and n be non-negative integers, let A be an m element set, and let B be an n element set. Then the number of all surjective maps from A to B is the following thing. The sum over all I from 0 to n, minus 1 to the n minus I, and choose I to the m. You can, of course, wonder to what extent this is really an answer and whether this is a closed form or something. Truth is, this is the best you can do in a way. There is also recursive equations, but this is definitely not worse than a recursion or not better than a recursion. Well, it is better, not worse. Anyway, there is no really closed form without a summation sign. So, this certainly beats listing and counting all the surjective maps one by one. So it's something worth proving. So, and again, I reference notes in the details, and in the notes I reference some other notes for even more details. I'm just gonna quickly sketch what's going on here and how you can apply this principle of inclusion exclusion. So the trick is, we know how to count all maps. Now we want to write surjective, so we want to restate the concept of a surjective maps in terms of a map that fails certain properties or satisfies certain properties. So, first of all, without loss of generality, assume that B is the first n positive integers. Well, B is just some random n element set, so it might not be the first n integers, but nothing will be lost if we just relabel the elements as the first n positive integers. Now, we say that a map F from A to B misses an element I in B if F does not take I as a value. If you're used to drawing maps by drawing the elements of A here, the elements of B here, and drawing arrows between the two sets, well, misses means that there is no arrow that ends up at I, which is why I call it misses. So it refers to that picture. Now, we let U be the set B to the A, so all maps from A to B. And for each I in N, we define a subset AI of U by AI is the set of all maps F from I to B that miss I. Or in other words, because missing means not taking as a value, so that don't take I as a value. And keep in mind that the set N, as we assumed, the set is just B. So we could just as well have said for each I and B. All right. So this is a set of all maps from A to B, and this is a set of some maps from A to B, namely the ones that miss I. Now, what are the surjective maps from A to B? A map is surjective if it misses nothing, if it takes everything as a value. So maps from A to B that miss no I in B. In other words, that belong to none of A1, A2, and so on AN. I mean, so we have defined the sets A1 and A2 and so on AN. And now the maps from A to B that belong to AI are the ones that miss I. So the maps that don't belong to any of the AIs are the maps that miss none of the I's. So in other words, these are the surjective maps. So in other words, this is maps from A to B without A1 union A2 and so on union AN. Sorry, the A in the AI has nothing to do with this A. This is just in order to match the notation from here. Okay, now this is just U. Okay. So how do we count them? The number of surjective maps from A to B. Well, we know the set of the surjective maps is this here. So the number is the size of this here. And this, now we can just copy, well, let me rewrite it as this here. And now by the principle, so by the principle of inclusion and exclusion, in the very last form, in this form, we can rewrite it as a sum. Okay, and now we look at what does it mean to be an X in U that satisfies X in AI for all I in I. Okay, X in U simply means that X is a map from A to B, because U is the set of all maps from A to B. Okay, and while we're talking about maps, calling a map X is a little bit confusing. Let's call it F. Just renaming the index. All right, let's go on. What does it mean for a map F to belong to AI? AI is the set of all maps that miss I. So F belongs to AI means that F misses I. Okay, now what does it mean that F misses I for all AI? It means that F misses all elements of I. Let's restate this a little bit further. All values of F belong to B without I. Why? Well, F misses all I in I means that none of the I in I is a value of F. And this means that that any value of F does not lie in I. So all values of F belong to the complement of I. All right, I'm just doing a bunch of rewriting here. However, this is something we can compute, because what is a map from A to B whose values all belong to a certain subset of B? It's simply a map to that subset of B. So instead of saying map from A to B whose values belong to the subset, we can just say map to the subset. And let's not call it F anymore, let's just say maps. So strictly speaking, I mean, this is a bijection really between the maps from A to B whose values belong to B without I and the maps from A to B without I. But you can actually pretend these are the same maps because they do the same things. They just have a different target. And we know how to count those maps. It's this here. Okay, and now this is a sum over all subsets of N. We can subdivide it according to the size of that subset. So instead of just summing straight away over all subsets, we sum over all K element subsets, and then we sum Z over all K. And K will range from 0 to N because a subset of N has between 0 and N elements. All right, so now that we have restricted ourselves to K element subsets, the size will be K. The size of A will be N, or no, M, because A has M elements. Now, what is the size of the complement of I? So B has N elements, and I has K elements. And since I is a subset of B, because I is a subset of N, which means the same, of course, as B. So because I is a subset of B, the complement here has size of B minus size of I. So size of B is N, and size of I is K. And so this inner sum here is a sum of several equal addends. All its addends are just the thing. So what the sum equals is the number of all K element subsets of N dot this addend. So let me rewrite this again, because this is saying how many addends you have, but all the addends equal to this here. Now this is an old question we know well how to solve. This is n choose k. So we get our first explicit form. N choose k times minus 1 to the k times n minus k choose m. And now we can message it into a slightly nicer form. We substitute n minus k into I. So I equals n minus k. So what do we get? N minus k becomes I, whereas k becomes n minus I. And yeah, k here also becomes I. Okay, this is by symmetry. This is n choose I. And this is exactly what we want, except it's common to put the signs at the very beginning, the binomial coefficients at the middle, and the rest at the right. That's just a convention. So I equals 0 to n, minus 1 to the n minus I, and choose I times I to the m. And this is what we wanted to prove. All right. This actually has a nice corollary. So to derive it, let me keep the theorem on the screen. Here is a corollary. And you might immediately see why it follows, because it's really just a corollary of the theorem. If n and m in n satisfy m is less than n, then this beast is 0. Why? Well, imagine an m element set A and an n element set B. So from the theorem, we know that the sum equals the number of all surjective maps from A to B. But the pigeonhole principle says that there is no such surjective map. So this number is just 0. The set from which the map is going is smaller than the set to which it is headed. So we cannot go, it cannot be surjective. Some element will be missed. So there is no surjective map, so the sum is 0. And finally, the equality case. So let's put n here. This is no longer 0, because this is counting the surjective maps from an n element set to itself. No m anymore, it's just one set. And those maps exist, but we know what they are. They are the permutations of that set. And so we know how many there are of them, n factorial. Again, that's the pigeonhole principle in action. It says that a surjective map from a set to itself is a permutation. So basically, if you have n pigeons and pigeonholes, every hole has a pigeon in it, then every hole has exactly one pigeon in it. There is no roommates. So the upshot is, from these combinatorial considerations, we obtained two nice little binomial identities. Actually, you might remember this one from a homework set. This used to be a homework exercise, except I to the m was an arbitrary polynomial of I of degree less than n. But it's basically the same thing, because an arbitrary polynomial is just a sum with coefficient of this I to the m's. But this is a different proof. So this is just one of many applications of the principle of inclusion-exclusion. Basically, the idea is, again, this is subtractive counting at its best. Instead of counting the surjective maps, we counted the non-surjective maps, the maps that miss some elements. Except we didn't, if we just straight away try to count the non-surjective maps, that would be just as difficult as counting the surjective maps. So instead of just saying number of non-surjective maps, we subdivided it according to maps that miss 1, maps that miss 2, maps that miss 3. And then using the principle, we also had to count how many maps miss several elements. So not just one I, but all I in I. But these things were all computable. We got those numbers. These were b minus 1 to the a. So we computed them. This became this sum here. And because there are several combinations of elements that could be missed, we got this n choose k. Generally, if you see a counting problem and on the right-hand side is some kind of sum with binomial coefficients and minus signs, you should think of the principle of inclusion and exclusion, because these terms are the kind of terms that come out of it.